Hi everyone, my name is Mirko Gelsomini and today I'm going to introduce you to Imagine, Embodied Learning in Immersive Smart Spaces. This work has been conducted at Politecnico Milano by me, Mirko Gelsomini, Giulia Leonardi and Franca Garzotto. This work investigates the pedagogical potential of Imagine, an immersive interactive environment for educational purposes where children are exposed to auditory and visual stimuli, activated by performing mid-air gestures and movements in a digital enhanced physical space. The system is remotely controlled by the teacher who can customize each experience according to a group of individual needs, modifying intensity, duration, and orchestration of stimuli and action stimulus sequences. Embodied cognition theories emphasize the relationship between physical activity and cognitive processes and are supported by a growing body of evidence from psychology and neurobiology. According to the hypothesis that embodiment can enhance the learning process, we have designed and developed an educational didactic experience within Imagine, aimed at facilitating learning of factual knowledge on a curricular subject. The experience is modeled following Kolb's experiential learning process according to the cyclic sequence of experience, reflection, learning, and is divided into the different phases of challenge and initial thoughts, resources, and assessment. In the very first phase, children are welcome in Imagine and the teacher presents a topic that will be discussed during the lesson, making use of images projected on the wall and on the floor. She then collects students' questions and elicits children's discussion from previous knowledge. During the resources phase, a 5-minute video is projected to the wall. When the projection ends, children are called in turns, one at a time, to perform a task, which consists of answering a proposed question using one of the given interaction types. Lastly, in the assessment phase, children are evaluated on their acquired knowledge. The structure of each single task was designed on the basis of textbooks currently used in primary schools. From the analysis, 5 types of frequently used exercise have emerged cross-cutting different subjects, which we have reinterpreted with a view to motion-based interaction. The first, the selection pattern, presents the user with an explanatory image of the question on the front projection and a variable number of response option cards on the floor projection. A star projected on the floor, placed immediately in front of the user's feet, follows the student's movements. In order to select the chosen answer, the child must place the star and consequently herself over the card corresponding to the option deemed correct. The child confirms her decision standing over the card for at least 3 seconds. The second pattern, the classification, presents the user with a set of images and a series of labeled boxes, both projection or the front projection. A virtual superimposed end appears following the preferred user's hand. The user is asked to grab, drag each of the images presented at the top of the screen and release each of them in the correct category, shown in the form of a box at the bottom of the frontal screen. The third case, the reordering pattern, presents the user with a series of images randomly ordered on the front screen. A virtual superimposed end appears following the preferred user end. The user is asked to reorder the option cards according to a sequence contextualized by the question. To reorder the cards, the child is required to grab, drag, and release each element until the desired sequence is obtained. A pop-up will ask the user to confirm or cancel the response given after 5 seconds from a last interaction. The identification pattern requires user to recognize a given object based on its characteristics. 2 different types of identification are supported. The fourth one is based on color and shape. A variable number of images are randomly distributed in the both projections. The user has to identify the item requested in question and select it by positioning her body or by moving and closing her hand. The fifth one is based on position. A variable number of images are arranged neatly on the front screen. The user has to identify the item requested by the question by moving and closing her hand on its top. The sixth one, the association pattern, presents user with 4 frames at the top of 4 items at the bottom of the front projection. Each frame contains 2 slots, one housing an image and the other empty. The user is asked to associate, grab, drag, and release each bottom item with the images present in the frames, placing the objects in the free frame slots. Once all objects are placed in the corresponding slots, a pop-up asks to confirm or retry. In order to investigate whether imaging can actually facilitate children's learning, a controlled experimental study was conducted. As you can see from the image, the study is based on the comparison between the learning process that takes place in a traditional classroom, on the top, and the one occurring in imaging, on the bottom, with the aim of comparing impact on children's learning achievements. 70 children from 6 to 8 years old were recruited. They were pairwise assigned according to performance on a pretest to an experimental group, on the left, subjected to the practice within imaging environment, and to a control group, on the right, subjected to the traditional practice based on the frontal book-based approach within the classroom. Both groups were divided in classes accordingly. This study investigates a main research question. Can learning benefit from an immersive embodied approach compared to the traditional paper-based classroom approach? A baseline test, T0, was administered at the beginning of the first week to all students, in order to establish homogeneous control and experimental groups. 2 learning sections of 1 hour each were held in 2 separate days of the first week, same amount of time dedicated to similar topics at school. A short-term test in T1 and a long-term test in T2 were provided on the last weekday of the first week and after 7 weeks respectively. Both imaging and classroom activities used the same exercises, proposed in the same sequence and with the same graphical contents. The immediate effect on intervention after 2 training sessions, which we refer as short-term retention, was evaluated based on changes in the values on the score obtained during T1 with respect to that achieved with the baseline test in T0. Short-term retention was significant for both groups, as they score an average of 18 notions. This allows us to state that imaging educational activities are a comparably effective teaching tool with respect to classroom approaches. We categorize each of the 2 groups into terciles based on short-term retention scores. The first tercile can be traced back to the children who have retained fewer concepts and therefore probably those who have encountered more difficulties. The third tercile is associated to those children who acquired more concepts, which we can assume have had fewer difficulties. Consequently, the second tercile represents the group of children whose short-term retention is in the middle range. Children belonging to the first tercile retain an average of 8 concepts in class and an average of 11 notions in imaging. Results are reversed in the third tercile, in which children, in the control group, learn an average of 27 concepts compared to 25 acquired by the children in the experimental group. In the second tercile, children learn an average of 17 concepts regardless of their learning context. Speaking about long-term retention, the values of memory loss, that is the number of forgotten notions between T1 and T2, show that students from the first tercile forgot an average of 7.7 and 6.6 notions in the control and the experimental group respectively. Almost the same difference occurred in the second tercile students, who lost 8 notions in the control group against 7 notions in the experimental group. The highest memory loss can be noticed in the third tercile, in which students who learn in classroom forgot between 8 and 24 notions, and those who practice in imaging forgot between none and 11 notions. In conclusion, each child memorized an average of 18 concepts in the short term and retained 7 notions while learning in classroom and more than 11 notions while learning and imagining in the long term. Children with more learning difficulties found it easier to memorize within imaging. The better outcome could be ascribed to the effect of a wide range of different interaction modes and the various senses involved, which allowed them to more easily find the learning modality suitable for their natural inclinations. In addition, the evident greater ease with which the teacher has carried out teaching sessions within imaging allows us to deduce that it is acted as a catalyst of attention, thus improving retention. Finally, we present here the conclusion and future work. The results of our empirical study are encouraging, as we detected improvements in participants' long-term retention skills that could be ascribed to the experiences in imaging. From a broader perspective, our research suggests that motion-based immersive technology to support embodied learning activities in regular school contexts is a promising approach, as smart spaces characterized by low-medium embodiment like imaging might lead to revisit existing educational processes as well as to reinvent new ones. In the future, we plan to leverage the potential of motion sensing technologies by designing full-body activities that make use of iconic representational gestures so to take full advantage of the affordances of imaging. We will expand the study to a larger number of participants who will be involved for a much longer time, tracking their performances within each learning session. Such research will also support the creation of a corpus of data on children's bodily learning, unique in this field and valuable for educational practice and research. Eventually, this environment still holds promise in supporting children with special education needs in mainstream education, given its plethora of interaction modalities and stimulus that can be carefully selected by the teacher to give special education needs children the best tailored experience. Concluding, we thank Polysocial Award, the Social Responsibility Program of Politecnico of Milano, and the Municipality of Honolulu for having funded the project. We thank also Ludomi team, the teachers and students at Istituto Comprensivo Statale Via 4 Novembre of Cornaredo, Milano, and Istituto Comprensivo Statale Leonardo da Vinci, Cornaredo, Milano. Thanks all.